Okay, we are rolling. Okay, today is just a very quick little lesson. I don't have a handout for it because it shouldn't take all that long. Basically, so we'll start with just a couple sentences here. The process of finding a derivative is called differentiation. So, when can I find a derivative? In other words, when are functions differentiable? A function is differentiable if it is continuous. So this gets us back to the last unit, right, where we had to learn when a function is not continuous, right? It's not continuous when the value of its limit does not agree with the actual y value of the function, or when it's approaching an asymptote, it's not continuous, right? So a function can only be differentiated in places where it's continuous and it has, hang on, that looks really ugly, a determinable slope. And that's basically the whole lesson. We're just going to look at some examples now. That's the entire idea for today. So you can see why we didn't bother putting together a whole little handout for this one. It's 2 sentences. But I can show you some examples, and we can talk about what that last point means. What do you mean? Where are there places where I can't determine slope? Well, you learned actually way back in probably grade 9 or 10 that you obviously can't take the slope of a vertical line. So there's one problem. But of course, notice if it was a vertical line, wouldn't be a function. So that's obviously not really the issue here, right? Because remember, the vertical line test would fail on any equation that when I graph it, it turns out to have a part that's vertical. So that's not what we're talking about. We're talking about there are some functions that you can't find the slope of. Okay, before we take a look at those, let me just go back to my Desmos here. All right, where are you, Desmos? Oh, wait, Desmos is over here. And there we go. Let me just drag this over. Okay. There. Okay, so we learned in our last lesson, or we concluded from our last lesson, that when you take the derivative of, say, in this case, I have a graph that's a power of 4, right? It's a quartic. The derivative of that will be a cubic. So how do you tell the difference? Well, this is a power of 4. This is a quartic because it changes direction 1, 2, 3 places. It could have a maximum of 4 x-intercepts. Okay, hold on a sec. We're back. Okay, so like I was saying, this is obviously a power of 4. Even if I couldn't see the equation, I'd guess that that's what it is because it changes directions 3 times. If it were up just a little bit more, it would have 4 x-intercepts, so that makes it a power of 4. It's even, both arms are going in the same direction. Its derivative, right, g primed of x, is going to be a cubic. And as you can see, yep, that's definitely a cubic. It has 3 x-intercepts. It's odd. It changes directions twice. Let's play with that a little. What if instead of this being a power of 4 graph, what if I changed it to a power of 3 graph? What would you expect its derivative to be now? Well, now I'm expecting its derivative to be a quadratic, and it is. I'm having fun with this game. Let's keep playing it. What if instead of a quadratic, or sorry, what if instead of a cubic, I start with a quadratic? And I guess I'll just, there we go. What do you expect to have happen when you do the derivative of that? And we've seen this already. It's linear. Okay, well let's keep the game going. I'm actually going to just put a constant on that. What if instead of it being a quadratic, what if it was linear? This we haven't seen yet. What's the graph of the derivative of a linear going to look like? If you only are a degree of 1, what happens when you drop a degree? You get a degree of 0. What does that mean? Any ideas? What do you think the graph's going to look like? Somebody at home got it right away. It's going to be a horizontal line. It's going to be a constant. Cool. Okay, so now that we're hopefully seeing this pattern and how derivatives behave, they're always 1 degree less. What happens if you try to take the derivative of that? Now, on the one hand, it is kind of degree 1, right? Because there's no exponent on this x here other than the exponent of 1. But absolute value does kind of make this a tricky proposition. What are you expecting? Well, remember what the derivative is, right? Let's go back to this guy. The derivative of this thing is the equation that represents its change in slope. Well, this thing has a constant slope of 2, which is why its derivative is just the line when x is 2. Back when this thing was a quadratic, right, its slope is changing as you go around, but it's changing at a constant rate. And that rate has its own slope, which is why I get a linear. So, okay, so now back to this guy. What's happening here? Well, it has a constant slope on this side that's actually different than that side. So if I take the derivative of it, hang on, let me change that to f of x now. Look what I get. Get it? The slope on this side of the graph is 1, and the slope on this side of the graph is -1. And I want you to think about something. Let me get rid of the black lines for a sec. They're kind of in the way. Everywhere as I go along here, right, the slope's the same. The slope's the same, the slope's the same, the slope's the same. The slope's the same all the way up there. Remember that slope can be also thought of as tangent to a curve. Well, you can't really take a tangent to a straight line. But you also can't take a tangent down here either. Think about what it would be like to try to say, okay, I'm going to draw a tangent line to this point 0, 0. Well, you kind of can't, right? What's the word tangent mean? It's the unique line that touches a curve at exactly one spot. So it's really easy to see where the tangent is on a parabola, right? The tangent, say, at this point here would be a horizontal line because it would exactly touch once. The tangent here would be, you know, some sort of line like this that you can see me kind of tracing with the cursor. But think about this spot here. How many lines could you draw that would exactly touch this exactly at 0, 0? Well, there's infinite lines you could draw here. There isn't one unique tangent. So I will add one more thing to our notes here. I'm going to say because you can't create a unique tangent line to a cusp, you can't find a derivative at that point. So cusp is a fancy word that just means sharp, non-curved direction change. like the bottom point of an absolute value. It comes down to a sharp V shape. It's got an angle. It's not a curve, it's an angle. You can't find the derivative at an angle because you can't draw a tangent there. Well, you could draw a tangent. You could draw infinite tangents, and they could all be different. So because I can't make a tangent, I can't find a derivative there. So that leads us to a couple things we can do. We can, let me go back to Desmos, we can kind of determine that the derivative for this equation here doesn't actually exist. It is not differentiable at the point where x is 0. Let me give you a different one. Here's a piecewise function. Well, the derivative of this part of it would be just a constant of, looks like a constant of -1. The derivative of this part would be linear because that looks kind of like part of a quadratic. The derivative of this would just be, well, let's see, it has, what kind of a slope do I have here in this part? 0, right? It's flat, it's horizontal. So that would have 0 as its derivative for that part. The derivative for this part would be linear again, right? It would be negative down here and positive up there, but it would, looks like it has a slope of, I don't know, 3x or something like that. So let's see, let's do the derivative for that. So this is h of x, so let's see, let's change this to, let me get the keyboard back here. Whoops, oh, hang on. Oh, there we go. Change that to h of x. So, okay, what am I predicting again? I'm predicting that this part's derivative will be a constant. This part's derivative will be linear, but going up because all these slopes go up. This part's will be 0, and this part's will be linear, and the linear will be negative on this side and positive on that side. So let's see if I'm right about that. And there it is. So at this point here, it's not differentiable because notice the derivatives have a gap. So it is not differentiable when x is equal to -2 or when x is equal to 2. If I'm tracing the derivative, let me get the original graph out of the way. If I'm tracing the derivative, I have a jump discontinuity in the derivative. And then it's all fine, and then it comes back up and it jumps again. So there's two places where it's not differentiable. Okay? It is continuous itself, right? This is a continuous graph, right? If I trace it with my pencil, I never have to lift my pencil. But these 2 points here at -2 and +2 are called cusps, and you can't find the derivative at a cusp because you can't find a unique tangent line at a cusp. So that pops up in your actual assignment a couple of times. There's a couple of questions. There we go. Notice here's a cusp and here's a cusp, so there's going to be a couple of jump discontinuities in the derivative. So G, which one is that? And then that pops up again in question 3, which I haven't assigned until now. Where is this thing not differentiable? Well, it's not differentiable anywhere where I can't draw a tangent. And as you can see, there's points on here where I could not draw a tangent because it's a point, not a curve. It's an angle, not a curve, is maybe a better way to put it. Okay, and then I think there's another question like that. Oh, no, not on this page, I guess. So there we go. So I'm only adding a little bit to your homework. So let me go to the blog now. Blog. So now the homework says, same questions as before. I'm not adding a bunch. I'm just adding those couple that have to do with that cusp thing. So now you can do 2 to 6. I think what did I say before? I'd already said 4 to 6. So I'm adding 2 and 3, and I'm adding 9 and 12 and 16. That's about it. Okay? Oh, and then there's that little worksheet that we gave you the other day where you could practice just sketching the graphs. I've already had somebody message me and be saying, how accurate do they have to be? Not very. All I really care about are the arms going the right way? Do you have the right number of valleys and hills? In other words, if it's supposed to be a cubic, you can't change direction 3 times or 4 times. And do you have the x-intercepts in the right place, which would correspond to all the places where the slope on the original graph is 0, right? So where the tangent's horizontal. Oh, and we have an answer key for that now. People were asking yesterday, hey, is there an answer key for this? I'd say, yeah, we had to make one, but it's there now. Okay, so there we go. Oh, I guess I can stop my video now.